Welcome, everyone, to today's webinar, Unveiling Gigabyte's Backdoor, Mitigating Infrastructure Supply Chain Risk. My name is Melissa Russell, and I'll be the host for today's webinar. A couple of things before we get started. We are recording the webinar, and we'll make the webinar as well as a PDF of the slides available tomorrow. And at this point, I would like to go ahead and introduce our speakers. Our first speaker today is Paul Azadorian, who is our Principal Security Evangelist, and he is joined by John Lucades, who is our Senior Vice President of Strategy here at Eclipsium. Gentlemen, the floor is yours.
Thank you so much, Melissa. It is good to be here today. We're going to have a lot of fun talking about primarily the Gigabyte backdoors, most of our content today, John, as you well know, and just for the audience's benefit. We will deviate into some of the history, some related things, in addition to some supply chain related things. I like to see where this fits in the supply chain kind of attack surface that I like to present in various outlets, right?
Yeah.
So we'll start with the overview. Talk about what we found. I don't think John or myself actually found it. It was our team. I don't know if you were involved with that. It was our team that found it. And we'll talk about how to fix it, certainly, and some lessons learned from the future and how to mitigate risk moving forward from a supply chain perspective and how that relates to coffee. So
coffee, of course, being the important topic that everybody's here for.
That's right. Got a whole slide on it.
Yeah.
So this is the digital supply chain attack surface. As I like to, I came up with this, I like to frame it this way. It kind of caught on here at Eclipsium, and I think pretty much everyone is using this as the attack surface as it relates to the supply chain. So I'll cover very briefly because I want to focus in on where we're going to talk about today, like where we are in the supply chain with this particular issue. So all the way to the left, we have physical. Now, I like to say that if I go even further left, I have like physical supply chain things, like the Red Cross needs to make sure they have enough bandages. When we get into IT, our physical things are PCs, laptops, servers, devices, those kinds of things that could have supply chain issues in terms of threats or risk or attacks, which are difficult to detect. I think, now, John, disagree with me on this, right? But in order to truly be able to detect a physical supply chain attack, you got to pop the cover and take a look, right? To be absolutely certain. So if you're ordering 10,000 laptops, that could be problematic.
And in fact, sometimes those techniques are destructive. I mean, sometimes you make a mistake soldering, desoldering parts. Sometimes you need to like get at something and you end up drilling through stuff. It's really not scalable. Although if you really want to know, that's what you got to do.
Right. And then we move into what I like to call pre-installed software that we also lovingly call firmware, that also mixes back into what we call software or operating system software, right? And I think that pre-installed is very accurate, right? Bob Martin from MITRE pointed at my laptop once and he was like, you had software pre-installed on that you didn't choose, that was chosen for you, and when you received it, it was there, and most people don't change it. And so that's what we mean by pre-installed software.
Some subset of that is actually stuff that you can't remove either, right?
Correct.
Like this is where we're talking about the actual firmware. You can reinstall the operating system, you can switch operating systems. But all of the stuff that makes that hardware work is something that you're not going to get rid of unless you want to break it or rewrite it or something really
I mean, technically you can mess around with it. It carries with it great risk, and nerds like us like to do things like that. But most people, are even through the operating system, John, when you're an enterprise and you're deploying 100,000 laptops, most people are like, yeah, whatever comes with the operating system, I'm not going to customize it that much. They're in more of a third-party application that is their interface into the computer in their daily work. We're on a Zoom call now, people use Slack. Those are the applications. Those also carry with it very much in a supply chain issues and risk and threats and all of those things, as we saw with 3CX was a really good example of a third party. That was like a I like supply chain attacks so much that I put a supply chain attack in the supply chain attack. There was multiple
Where's the
levels to
meme?
that. Right. And then, of course, we've got the software supply chain problem, where roughly 70% of the code that most people write today isn't theirs. It comes from somewhere else. Someone else has written it, whether that be AI that's writing it or whether that be open source or some combination. More, I think, speaks to the non-AI aspect of it, where I'm incorporating libraries into my software. So today, in the supply chain attack surface, we're going to be talking about primarily firmware and how it interacts with, we'll call it the operating system. I think it is the kernel that, does it go through the
Bootloaders,
kernel?
kernels. I like the
Bootloaders,
way
kernels?
you
Yeah,
circle.
yeah. But I think in today's story is primarily the interaction between firmware and the operating system itself.
That's true. And the other thing that's interesting about this slide that's good to keep in mind is that this is a spectrum. There are sort of arbitrary lines that you can make a definition of what firmware is and where it ends and where it begins, but they kind of bleed into each other. And when you sort of move over to the right of this diagram, you start getting into stuff that users are tend to be more exposed to, or a larger number of users are exposed to. When you go to the left, you're talking about things that fewer and fewer people tend to have to deal with, because they're trying to the whole game here, like when we study computer science and stuff, we're talking about abstracting this stuff, and the
Right.
whole premise is that you don't want to know about each capacitor on the board. Somebody does, but
Somebody does. Like the researchers that I thought was interesting, they figured out how to bypass the BIOS password by
yeah,
shorting the pins on a specific chip. And I want to say, if you see that, you're like, oh, Eclipsium talked about firmware stuff and hardware stuff. I don't recommend that you start shorting pins with a screwdriver on hardware that you care about. Like, that is not my recommendation. You can damage the hardware. Ask me how I know this.
nice.
Yes.
Yeah.
Okay. So the Gigabyte firmware problem, I break this down into two areas. And the first one is well, it's interesting. We can call it, people call it a bug. I actually really do think it's a feature. And
It was intended to be.
It was intended to be a feature. So
Yep.
Gigabyte firmware includes a Windows executable that uses a standard method to deliver the payload to a Windows system. I'm not sure if this works. Is it documented to work in Linux, or is this just like a Microsoft? This is just a Windows thing
It's
because of the tables?
used in Windows. I don't
Yeah,
know of any Linux that actually does it, but it could,
it
because it's a
could
standard.
certainly.
So there's a
Yes,
standard ACPI table that handles this, which we'll cover later. And
yes,
anyone could implement that. I don't think they do.
right. Yeah, I think this is just Windows. Also, this standard method that we'll jump into a lot more details. Basically, it was, I want to say, created by Microsoft because they didn't trust all of the firmware vendors to create a standard way in order to do this, and they feared that every single one would have their own method and we'd have 12 different problems rather than one standard way, that we could have standard ways in which to also fix that problem. Did I capture that correctly? Is that your understanding too, John?
It is. I think we'll get into a little bit more detail when we describe how it works.
Yeah.
And what you're really doing is motivating why, which is important,
Mm-hmm.
because why do we build a thing that lets firmware drop files to a operating system startup process, right? Like that breaks this whole arbitrary line that I decided to draw between firmware and operating system, right?
Right.
But you're going to do this because there's various features that actually use that make that really useful. Like if I want to manage a system, and if for whatever reason that agent gets corrupted or removed or whatever, I want it to come back. Well, that's actually what this feature is for. And if you try to do this and there isn't a standard, you and a hacking activity are doing the same exact thing.
Correct.
So now we'll make a specific way that we know that it's supposed to work, and that's the That's the way you're supposed to do it. And so that's what this is, except it really still does do the same thing that a hacking activity is trying to do.
Yeah. When you were
And that's
describing
the
that,
fun
John,
part.
I was like, John, are you talking about a bootkit or are you talking about this functionality that's supposed to be
That's
there?
right.
Yeah.
That's
This,
exactly the point. We got a slide for that later.
yes. So the executable, so this process, right, goes from firmware into the operating system. Once the software is running inside the operating system, this is where further issues were found that speak to how an attacker may attack the process that was put there by the firmware, right? So
And that,
how it operates, what it does and does not do, creates certain vulnerable conditions that an attacker can take advantage of. So those are the two high
yeah.
level. This is
And
the problem we found.
if you relate the rationale as to why, you kind of come back to this is why we have that standard. And this is exactly the sort of things we're worried about when we look at a standard that lets you have firmware influence the operating system. The sort of things we specifically are afraid of is
Yes.
somebody going and downloading random payloads, not random, but payloads that aren't verified, that aren't right, and then getting to run that with high privileges during the startup process. That's kind of bad, actually.
And was the executables that are put there, John, is there legitimate intention to update the UEFI firmware?
Among other
Or
things, it's
or
actually
also drivers, right? Because if you've got a Gigabyte, motherboard, right, it may have other drivers inside of Windows that
drivers,
you want to.
applications. It,
Yeah,
it itself is an application. That these updates that any OEM would have include a lot of different things, and they are the source of that information. So they kind of need to have a way to push that to your machine. You need to be in control of that. And to be fair, you are in control of certain pieces of this. The problem is that you don't expect that a updater, when removed, is coming back. And you also don't expect that an updater is going to insecurely download and execute stuff from the internet. You
right.
expect updaters to be secure. They're that, you set up the castle and you set up the drawbridge and the moat and all this stuff, and you kind of expect that everybody's looking at the updater because that's the thing, that's the one way that's supposed to be in, right?
Right.
Eh, you know,
Eh,
unfortunately, we have a lot of these.
yes. So if this sounds familiar, there have been bootkits essentially that have used this method and other methods. I would say, John, I know you're
Called
very
similar
familiar.
methods.
Yes, similar. We'll call them similar methods. I know you're very familiar. So the CompuTrace backdoor is very similar to this in that from firmware, they were executing something in Windows, but that was to track the location of the
So
device, right?
CompuTrace is exactly the reason why this was created, because it's a feature. It's designed as originally was for finding lost laptops,
Right.
right? And so you have a feature, and by the way, if you're looking at that use case, it's a lost laptop. It might have been a stolen laptop. The user in front of it is potentially malicious. So you want this thing to come back after it's been reinstalled. You want it to come back as soon as it touches the internet. You want it to like bypass all these things and somehow work. Without a known way of doing this, if you think about what Absolute has to do, they actually kind of have to hack the operating system in order to make that happen,
Right.
which is fascinating on a few levels. Even if you are doing everything well, what's Microsoft going to do about that? How are they supposed to respond to that? Because they can't tell if you're using the same technique as, Hacking Team or some other APT. This makes it very hard for them to fix things, and
Correct.
so without breaking a legitimate feature, so they had to create a mechanism that allows Absolute to do its job, but do it in a way they know about, and they can actually start to put protections on. Now, the quality of those protections is a matter here as well, but that's the whole sort of point. If you think about, though, why does an attacker want to do this in the first place, you can look at these examples of like a hacking team and Mosaic Regressor, and you can see that it's a persistence mechanism. It's this lovely thing that brings you back every time you reboot the machine. Even if you've reinstalled the OS, even if you swap drives, whatever, it's baked into the motherboard, and every time you are booting the machine, you get your implant right back.
Unless you put Linux on it.
Apparently.
But most of the like hacking team and Mosaic Regressor are Windows binaries they're trying to put in the chain to ultimately insert into a Windows kernel. And so if you're running Linux, you're way more secure in this case.
Well, I wouldn't say you're more secure. I'd say that you will bypass, you will break the process that they have created here.
It's a good point. Yeah.
But you could do the same thing in Linux. And
Absolutely.
in fact, the fascinating stuff about when you look at shim and the secure boot stuff in Linux, there's a way to do the same stuff. It's just you're going back to, there isn't a standard like WPBT that makes everybody do it the same way, and it's sort of understood. Right. Now you're just hacking stuff.
Yeah. So speaking of WPBT, this is a fascinating concept that we've kind of described up to this point as at a high level, but it's the Windows platform binary table, which allows for, again, very similar to a bootkit as we described, allows for firmware to install binaries inside of Windows, do this in a standard way. It resides in memory. Is it the ACPI tables that allow the firmware and the operating system to share files together, essentially? That's what it's accomplishing?
Well, so WPBT specifically is about sharing a file. It's about passing a file. I would say all the ACPI tables, like what they do is pass information from firmware to the operating system.
Right.
And you need that for all sorts of different reasons. And
yep.
Firmware configured things a certain way. Here, let me tell you how I configured it. That's what ACPI is all about. Here's a file that I think you need to use. And so that's basically what WPBT is doing. And there's a certain way that certain OS boot process code is going to take from that table, check things, and put it in certain places. And that's the premise. That's how you can make something like absolute CompuTrace work. Mm-hmm. And that's why it's an official standard. Now, what Gigabyte did is actually implement that standard and used it for their updater. Now, on the surface, there's nothing wrong with that. However, I think what ended up happening here is something that most people wouldn't expect.
Right. So let's do one more flashback reference, because we talked about the Windows platform binary table back in September of 2021 in what I would call our now infamous "Everyone Gets a Rootkit" blog post, which I love the title. This was before I joined, but I love the title. And this post got a lot of coverage from various outlets because they're talking about the Gigabyte thing that we found. But I found also everyone went back and said, oh, Eclipsium also talked about this Windows platform binary table, as we described. It was introduced in 2012 with Windows 8 to create this standard mechanism. And so we talked about it. John, what was the gist of this research?
Well, so the fun thing is that if you go back to that blog, you'll see that we're not the only ones who kind of look at this feature and say, sounds like the official mechanism to create a rootkit that will be supported going forward on all of these versions, which, as a security researcher, you're going to think that way. And it's not wrong, but it is also not necessarily the story that explains how somehow you have to make these features work. How are you going to find lost laptops? If you have another solution, then you're going to need to somehow get the community on board with that other solution. This is the solution that exists, and it has these problems, right? One of the problems is how, when you look at something that's going to be baked into firmware, the odds of you having that thing way longer than any version of an operating system that you might think of. Just imagine all the old hardware that you, Paul, probably have, that you install the latest version of some Linux on it, and you kind of do expect it to work, right? And all these features that were working before should continue working, right? Well, that makes it really hard for you to have a certificate that expires at a certain time and have that certificate signing the thing that's in firmware. And if that
Oh, I
isn't
see.
going to get updated all the time,
Mhm.
you're going to have to accept some certificates with really old stuff in it. Oh, you remember back when SHA-1 was the way that we, hashed and signed all this stuff?
Mhm.
Oh, so now I got to accept SHA-1 because your old stuff was released back when SHA-1 was the right way to do it. And so you get stuff like that that becomes problematic, not on most operating systems in most cases, but because this is persistent in a way that outlives what everything else you're going to do, it becomes a problem for, everything, because it's sort of fundamental. It's the startup process, right?
And the binary that is in the firmware has to be signed in order to run on Microsoft Windows, except in 2021 we found that that may not be true, that
But
binaries may be accepted that weren't signed or were signed with expired certificates.
signed, but the rules for what is accepted are different.
Right.
And so that's kind of the point. So like, actually, if it's unsigned Windows 7 and before stuff, yeah, it's probably just gonna break.
Yeah,
But to be fair, it was gonna break anyway, no matter what you did, because
sure.
like there was other stuff the signature process itself was gonna break stuff, and they have to draw a line somewhere and say, no, from this point forward, it has to be signed. So even if it did manage to drop the file, you're dropping an unsigned file that's not gonna run. Okay, cool. Problem is that you have to make compromises here somewhere, and these compromises are what get you in trouble from a security perspective.
Right.
Because in a way, it's like two sides of the same coin. Whatever you do, somebody's going to have a bad day. If you go and you make it maximally secure, stuff don't work. That's a problem. If you go and you secure it and you leave open some of these things, then you have basically standardized the exploitation path.
Mhm.
Thank you very much as an attacker.
Right. So let's talk about, well, the exploitation path, but this is also describing how the feature is supposed to work, which is what I love about
Isn't that cool?
I just love about when I did this diagram, I'm like, oh, this is the exploit. No, this is the path that it takes because it's how it's supposed to work.
Can I just say right there, that's my favorite kind of
Yes.
vulnerability in
Yeah,
general.
you're living off the land, right?
It's the most difficult to fix. It's the most interesting as a security researcher, it's sort of you're backed between a rock and a hard place. There's not a lot you can do other than accept and monitor this sort of risk, because this is just the trade-off, right?
Mhm.
Like you could do it another way, but then you just have a different trade-off.
Right. So, John, can you walk everyone through this? Because I read our write up on it and I attempted to diagram it, and I had some things backwards. So I want you to
No,
walk everyone
I'm
through.
happy to.
Yeah, thank you.
I think what's fun about this is I'm particularly proud of it, even though I'm not the one who found it. But I'm proud of it because it wasn't a manual activity to find this. It was
Mm,
our product doing what we built it to do and bubbling up some anomaly that we didn't expect to see. And then we got the manual, security
mhm.
researchers involved, and got dug into it and figured out how it was working and what it did, and found all the problems that were related. But what it started with was an anomaly in UEFI firmware. And so we do these.
That our products consumes, like we scour the internet. We're kind of
Yeah,
like people collect weird things, we collect firmware, and we scan that
yeah.
firmware, and we scan some of this Gigabyte firmware, and we're like, something's wrong. The product said something's wrong
What is
here.
up with
Yeah,
that?
what is up with this? Then we did manual investigation, and we
Bingo.
found basically this is the process that was happening.
And we are talking about UEFI right now, but every supply chain works the same way.
Mhm.
There's a bunch of stuff. that is effectively abstracted that happens earlier in the supply chain. And you don't have to think about it because that's what you're paying someone else to do. Like
Right.
that's your supplier is doing this for you.
Mhm.
Every supply chain issue kind of looks like this if you back up enough and you stop looking
Right.
at all the specifics. And the premise of what we were trying to do when we found this is the same thing you need to do with every supply chain, which is to sort of look through it and find the anomalies, try to find the things that aren't as you expect them to be. And when those expectations are violated, that's where the interesting stuff is.
Right.
In this case, it's interesting when you're dropping Windows binaries. Why?
Yes.
Because Hacking Team did it, because LoJax did it,
Yes.
because
Yes.
like this is just a thing that attacks tend to do. And it's, in my opinion, it's sort of the dumbest thing to do, but as an adversary, that's always the first thing you're going to do. Why am I spending more time, more effort, making things complicated and breaking in different ways when I can make the most simple thing happen and go right back to everything everybody understands and do the
Right.
one weird, crazy trick, dropping files into Windows from firmware. And I don't have to worry about all the other stuff, right? That's complexity I don't need. So that's what they did.
So, John, where does this process start? I'm assuming I'm going to guess that in the driver execution environment phase of system startup, that there's some kind of standard. It reaches a point where it's like, hey, do I have a binary that needs to be loaded, right? And that's a standard in Vue EFI that we reach this phase, and this is a checkpoint to go, oh, I'm in this phase now. The next thing I'm going to do is I'm going to see if there's a binary that needs to be loaded.
Let me jump back just a little bit and sort of explain. You have all of these phases in UEFI, and one of them, after you've initialized a lot of the hardware and you get into some sort of a stable environment that looks like a computer, you go through Dixie, or the driver execution environment. And in Dixie, you basically iterate over a bunch of modules. And you run these modules and they do whatever it is they're supposed to do. They can have dependencies, they can do all these things, but one of these modules is going to go and prime an ACPI table WPBT, which is the thing we've been talking about. And
Right.
what it's going to do is, based on this enabled flag, it's going to either load or not load a what is really a Windows binary. But as far as UEFI cares, it's just a bunch of bytes
It's right.
into
Yeah,
a table in memory.
Right.
That table
Right.
happens to be the ACPI table WPBT, and the OS happens to know, if I see this table, here's what I'm going to do with it. And that's where it actually drops it to disk itself in the operating system and causes it to execute as part of the startup process in this case.
So it goes into memory first. That's where I had it wrong. And then the operating system puts it on the hard drive, and then
Bingo.
the SMS
And then launches it later.
Right. Launches it using the Windows Session Manager.
Exactly.
And
now
the flag, I'm sorry, John, I want to go back to the flag that it's checking for, the App Center download and install. That would be a setting that you probably would see in your BIOS if you were to.
That actually is a setting in the BIOS, and that's one of the things that we recommend you turn off if you have one of these boards.
Those are just values stored in NVRAM, essentially.
Yeah, that's it. It's just a variable.
Yep.
Enable,
it's just
disable,
a variable in NVRAM. I got you.
Yep.
Okay.
And it's accessed through that startup menu when you like push F2 or something as your system is booting, and you go into the BIOS settings, and somewhere in there's a App Center download install. That's what they call it.
Yep.
And that's the flag that causes to happen or not, which is one of the defense mechanisms. Is until you've updated this thing, you should turn that off, because what it's going to drop and run is not a great idea. Now, the new version is probably fine, but that version, maybe you don't want it to run.
Yeah, it was really interesting to me to unpack exactly how this process was working under the covers.
And this is where that old everyone gets a rootkit WPBT research it really comes into play. Like, this shows you how it's being done, even in an official intended way. But this also shows you the flip side of that coin, where these are the sort of things that can go wrong. when you do it, right?
Right.
Even if you do the right thing, so to speak, these things can go wrong.
Now, the GUID, John, we didn't talk about that. That's really just the identification string, so that when the
Mhm.
Dixie driver runs, it goes, I'm
It
gonna
finds
that
this.
yeah, that's how it finds it, by that unique
Yeah.
identifier. So if it's enabled in the NVRAM variable in the BIOS, it knows I go to this GUID. In that GUID, it tells it that this is and that's actually the GUID and the binary for the Gigabyte
In the bio.
issue that we're talking about, right? So that's the
Yeah.
actual GUID, and that's the actual binary file
Yep.
name that we
If you go
discovered
and
in
you
there.
parse the UEFI file system, so to speak,
Yes.
you're going to get these GUIDs representing these files in sections and volumes of the firmware
Right.
itself. And so that's actually what we do when we do this analysis. We go and look at all of these images, we parse them out, we figure out what's there, and then we run some heuristics on them. We sort of check if they're normal. And when you find this, you say, what the heck are you doing? And then you go figure out what they're doing. And you say, that's cool, except, and that's where we get to the next slide.
Right. Okay, but this is great. So we're in the point in the story where the system has booted. Now we all understand how inside of firmware there can exist a Windows binary that is now running on the operating system with I'd deem it as a high level of privilege, because I think the answer is it depends what privilege level. It can depend on
Fair.
how your operating system is configured, which
I
version
call it
of
high
Linux
too,
that you
though.
have, right? That's kind of a cop out on my part, to be
I
quite
mean, no,
honest,
no,
right?
it's accurate. I think that there's always a debate here about what you care about. And to be perfectly honest, it's not, no one can make the generalization across every possible thing.
Right.
In your environment, doing whatever it is you're doing, it may or may not actually be something that matters in a critical way, right? But in general, I use the abstraction that says you probably depend on operating system security controls, right? For a lot of things. And if this bypasses them, then it's kind of critical, and it does.
Right.
So therefore, I say it's high privilege. But
Yes.
you edge cases go here.
Yeah. Okay. So the three URL. So there's actually three. So this is the first URL that when this service starts up, does it check all three, or does it depend on the version of?
There's some configuration that tells it which thing to do.
Okay.
But that gets a little complicated. So we didn't go into all of that, but it's going to do one of these three. And the bottom line is that no matter which one it's configured to, it's pretty bad.
It's pretty bad. Yeah. So the first one is, as everyone can see there, is it's going to a URL, and it's not using HTTPS, it's using HTTP, which could allow an attacker to perform some kind of man-in-the-middle attack very easily.
Right. And everybody knows that. That's just an HTTP thing. Every time everybody who does some amount of cybersecurity knows that. And if you look at a link and you don't see the S, you're already questions should be appearing in your mind.
Right. Now the other two URLs that we discovered that this service was accessing are using SSL, but I've got more bad news.
Yes, you do.
The remote server certificate validation is not implemented correctly, which allows for man-in-the-middle attacks.
Yeah, it's basically not caring what kind of certificate you give it back.
I see.
So the fact that it's checking something is sort of irrelevant if you will allow anything that it checks.
Oh, so it's not even like it's all validation of that server certificate is just not being done.
I don't recall if there's some things that it might be checking, like you might have to have a certificate that hasn't expired, right?
Yeah, okay.
But what it's not doing that's critical is it's not actually checking that you really have to a trusted root download.gigabyte.com as like a thing that a trusted root actually issued to you. It's that part is the part that you can spoof just by making something else.
Now
making it yourself, I mean.
Right. The host name is interesting in the final URL there on the screen. Software-NAS is that could manifest itself as a host name that you put in a host file. That could
Yep.
be a NetBIOS name or a Windows
Yep.
name inside of your Active Directory environment. It could be a number of things that would
You
make
know,
it
when
easier for an attacker to man in the middle of that, because I don't have
right.
to, it doesn't have a fully qualified domain name, so I don't have to worry about DNS.
When I was talking to some folks about this issue, we talk about sort of what are the scenarios where this might happen easily to random people. And I like to bring up the coffee shop, right? Where you go to what we would probably call in more of a technical sense, an untrusted network. But it's really just joining someone else's network. And if someone else creates a machine on that network with this name, most systems, unless configured not to, are going to search the local domain name, the local, local network for a machine with that name. And oftentimes the way that'll happen, like in Linux, is that you'll have a search domain that you'll append to software.net-nas, and then you'll ask DNS for, what do you got? Well, if your DNS is the wireless router that you just connected to, and it's going to append .local to it, I don't care, whatever, then your fully qualified domain name is going to be software.nas.local. And it knows that it's resolving anything .local. And anybody on the same Wi-Fi with their name happening to be software NAS shows up in DHCP and gets resolved. Now, this is a configuration of the router problem, but
sure,
you are at Starbucks and you don't know what their router is configured to, or you just went to a friend's house or whatever. Somebody names their machine software NAS, and now you're going to go to that machine. And by the way, not only like the previous one, it wasn't checking some of these the validity of the certificate all the way down to the trusted root. You can't do it with this one. There's no such thing. There's no root to like give you software NAS. So if it's going to accept any of them, it's going to accept all of them. And so that's the issue with this last one, where the realistic scenario is amounts to you and I go to the same coffee shop and I name my machine software NAS. Right. I'm going to own you.
There's a little history behind attacks that work very similar in Windows environments.
Right? Exactly.
Of that very similar kind of name resolution for a service. One was for like a proxy. I don't remember what they were, but yeah.
Yeah, I think this concept goes way back, and it's sort of a problem that in a sense you're just doing it wrong from an updater perspective. Like your updater should not do this stuff. It should only support a secure mechanism. And back to that castle analogy, this is the one way in and out. You better have all your eyes on this and only allow the right things. And 3 different methods, 2 of which can never be secure, is probably not what you're after.
And now when the software reaches out to these URLs, is it looking to download specific files? So I basically just have to serve it the file that it's looking for?
Yes.
I gotcha.
And that's where we kind of get into the next slide. And what it's going to expect to download is a payload, so to speak, something to run. And it is supposed to be signed, but it's supposed to be signed in the same way that anything that Windows runs is supposed to be signed. Yes, you can turn that off. Yes, you can pop things up to the user and say yes. But realistically, if you can write something that runs normally on Windows, that's what it needs, right? So give it one of those, call it the right name, and it will go do it, right? And that if I were building a first stage payload, it would do more or less exactly what this does. And I would use WPBT because I know it's going to work all the time because it's a standard mechanism. And so what you end up with, and this is what, if you sort of think through what goes through your head when you find stuff, like when we're looking for weird stuff in UEFI firmware, and we find what amounts to a first stage, malware environment, right, in firmware, we get a little excited, right? That happened.
Sure.
So we kind of looked at this and said, oh my gosh, this is basically a first stage payload. Yes, it looks like it would be valid, but can we even tell if Gigabyte really did this or somebody else made it look like Gigabyte did this?
Yeah, that's where I was
Can we
going. How do we
tell?
know? Yeah, how do we know if this was
Right.
a legitimate Gigabyte thing, or if there was a supply chain attack and it included Gigabyte, that malicious actors were behind some of this potentially. Now we don't have any evidence, but we do know
And
Gigabyte did suffer a
at
breach
this point,
twice
yeah,
last year. Was it both last year?
I thought one of them might have been this year, but either
Okay,
way,
it was
it's
twice. It
still,
recently, in other words.
yeah. But and so we had to and this also happened while the MSI breach was kind of going on, so we were already kind of excited. Now we talked to Gigabyte. They did acknowledge this thing. They have documentation about this thing. It sounds like it was a legitimate feature.
Okay.
So I don't want to overextend the way people are thinking about this, but at the same time, it is the kind of thing we wouldn't be able to tell without somebody who seems to have some sort of official email address, I guess, telling us that it really was. So this is the sort of thing that, again, let's take a step back out of this issue and look at supply chain in general. That's what you're looking for. That's the whole premise behind trying to validate the supply chain, is to find stuff that doesn't do what you would expect it to do.
Right.
Now you got to do an investigation and you got to sort of figure out, all right, was it actually, all right, they probably really did this. All right, you did this really badly. Like this is really, but this is a really good first stage payload for a rootkit. And it's probably a really bad updater, right? That sort of thing is what you're saying.
And so the executables that it downloads are not signed or validated?
They are signed, but they're signed with the same kind of key that you would use to build any Windows binary.
Oh, okay.
In
So
particular, there's no check that it is a Gigabyte file, right? A Gigabyte signature.
So they just need to be signed. So I need to correct on the slide. They need to be signed with a Microsoft Windows
something that Windows will run.
Yes, sure.
You need a special kind of certificate to do this, but anybody could get one, right?
Right. Or steal. Attackers will just steal one.
Right. Or
find one.
And in fact, what I really like about this from an adversary perspective is that it basically is a deployment mechanism for your living off the land attacks. If you take any valid Windows binary that people really do use for something, the fact that it shows up isn't going to surprise anybody unless they're really looking for this. You know what I'm saying? And I think that has worked on a lot of levels, regardless of firmware or anything else. Living off the land is one of the ways to do stuff these days. Do those techniques, get it persisted by firmware, and use your command and control that looks like a Gigabyte update. Oh my gosh, that's pretty cool.
I wonder if, I'm just thinking out loud, if you could feed it a Linux binary and use WSL to run the Linux binary.
You could, but WPBT I don't think gets processed, because technically WPBT, the W in it is Windows.
Yeah. Oh, so I meant in the downloader. If I have the downloader download a Linux binary, does that get around the signing thing?
I mean, if you manage to make the downloader run, yeah, sure, probably does. But I don't know anybody who would do that.
Yeah, be interesting.
You could make it work though. I'm pretty sure you could.
Yeah, be interesting
with wine and stuff. Yeah.
So you did mention MSI.
Now this is different than MSI in a couple of ways, but it did happen around the same time.
Well, and specifically, I wanted to draw upon the signing example and talk about firmware that it's signed. So there's multiple things that are potentially signed or not signed, right, in this whole process. The original binary, the binary that is in the firmware, right, is something that should be signed. The payloads or executables that get downloaded once it runs also has some signing process, like should be signed. If one of those updates is firmware, for, let's say, UEFI, that should also be signed. But as we looked at MSI, who leaked 1.5 terabytes worth of data, we found and published that largely those firmware images are not signed, which is,
That's right.
that's very dangerous, because that means I don't
So
need to, in order for an update to happen, I can create my own firmware and I don't have to sign it.
let's talk about each of those stages for a second. In the firmware itself, there's a certain amount of, you need to trust what's there going on. At some point, you either boot or don't boot a computer, right? And if you don't boot a computer unless it's, you can set it to do that. That's a thing, but you may brick it if you do anything but the signed firmware. Sometimes that's what you want, and there are computers that are set up that way, right? But if you've got a general purpose computer and you want to leave it open to somebody to do something with, well, you can't. You got to run whatever's there. And so that is where the root of trust comes in. Sometimes you don't have a hardware root of trust. You just trust whatever's in the SPI flash, and that's the thing that's going to check everything else, right? If that gets owned, you're done. Most of these systems do that. Sometimes you have boot guard, which moves that root of trust to hardware. And now hardware checks the first stage of what's about to boot. And okay, now if it doesn't validate, what are you going to do? There's a policy question there, and it becomes
right. But
problematic
boot guard,
where you brick stuff.
Boot guard is a different level of trust
Signing.
and
It's still
signing.
signed.
But from a capsule update would be signed also
That's later, actually. So
that's okay.
This is talking about what's in the board right now. Now let's keep going, and you're going to get to the update next. You're going to say, well, when I replace what's in the board, I want to check a signature on the update, and that's where capsule comes in. But in theory, there's a bunch of ways to do it. Different manufacturers have their own things, whatever. If it's signed at that time and protected in the board so that it can't be changed, then that sounds like a good process too. What MSI did here is that almost all of them don't protect that image. So even if it was signed, I don't care, because I can just rewrite it. And so unless it's protected, the signature is meaningless, right? So 800, NIST's special publication 800-147 was like 2011, where they talked about this issue. They talk about, you would need to sign your firmware. Here's the requirements. And by the way, when you do that, it has to be put into this protected space. If you don't protect it, you're breaking that part of the requirements. If you don't sign it, you're breaking the other part of the requirements. Does that make sense?
Yes.
And so this is where, if you have a manufacturer where one or the other isn't done, it's sort of irrelevant. You're trusting whatever's there, you're just going to boot it, right? And so that's where, even if I did sign some of these things, they didn't matter, and they don't, right? And so if you get into back to Gigabyte, that's sort of different, because we are talking about things that are signed, but now we have problems with how the update payloads are verified. And so your signing was irrelevant. You see what I mean?
So so explain that last part again. So if the update process is downloading firmware,
and it's going to get it over TLS, right?
but get it over in insecure mechanisms, which means an
Exactly.
attacker could supply firmware.
So I can supply anything I want to you. And then when you receive it, what you actually are checking is the same thing you check for any other binary that runs under Windows, and nothing more restrictive than that. Then all you're telling me is I'm running something that can run under Windows. Cool.
Right.
You know what I mean?
And then
so that doesn't actually do anything, even though you're running a bunch of crypto.
And the attacker can do whatever they want at that point, including firmware updates.
And well, it depends on the firmware update part. There's other parts that could be checking that, but even if it were the case that it was not checking all of that, you now have a way to persist anything you want to run in the operating system. So all those things that firmware was trying to protect, including itself, they kind of don't matter, because you got a feature that allows you to do anything you want to the OS. I don't
Right.
need to get firmware anymore. By the way, it's
Yeah. Oh yeah.
persistent
I think
too.
that's very true. It's yeah.
How
What
cool
I
is that?
wanted to do with firmware is already done for me as an attacker.
Right, like
Yeah.
you built that in. That's amazing.
Right.
So
Unbelievable.
this is the problem with the whole issue, and this is why we sort of use the word backdoor in a lot of it, because what is a backdoor? I like to look at supply chain attacks or issues in two different categories. One is a tampering category where you put something there, but what I actually received is different. Somebody messed with it, changed it, added stuff, broke stuff, whatever. That's not this. This is the other one where it was built that way. That's the actual thing. It wasn't tampered with, but the thing is flawed in such a way that other people can go and do things I don't expect to my system. And in this case, anybody can go and spoof the Gigabyte updates and cause them to cause whatever they want to run on my system. That is not something I ever expect to happen. Does that make sense?
Yes. Yeah, I think the piece I was missing for a moment there was I don't have to persist in firmware because it's already there for me.
I mean, you could do that too, but
Yeah.
but back to the whole like do the
But I could
simplest
do
thing possible, right?
I could do other. I mean, I could start looking at how I use this mechanism to update other firmware, such as my EC
You can.
firmware, which is my
And that's
embedded
one of the things
controller.
we saw with MSI. They weren't
Right.
signing this other firmware stuff. And so you could go after that instead.
And this is my fear. I mean, let's use this attack path as an example. An attacker goes, well, that's neat. I'm going to give you a binary, and inside that binary, it's going to update the EC firmware because I have this level of privilege now. Maybe I might need to escalate a little more depending on the system and how it's configured.
Maybe.
But I'm going to use this mechanism that's there to overwrite and write new firmware to your EC controller. That new firmware, since your EC controller controls your keyboard, right? That usually that microcontroller controls the keyboard. I'm going to put a keystroke logger in there.
Once you get that, you can do all sorts of things. It's actually it's very powerful. And that's actually where this whole below the surface thing comes from. It's the whole idea that all that stuff that you depend on but don't know what it is really interesting both to attackers and defenders. And the problem for defenders is that there's no way they have time to deal with all this.
Right.
They have to rely on something to deal with it correctly.
I think the only thing we didn't talk about in this slide, John, was that I think we need to underscore again is even if you, let's say you go into the BIOS and you disable this feature. So I'm talking about number 5 on the current slide. I disable this app update, Gigabyte app update, or whatever they called it, and then because I listened to Eclipsium's advice and other people's advice that I should update my firmware, I'm going to go and update my firmware. And updating that firmware reverts that setting and turns it back on. I boot the operating system, and I get this lovely service that's downloading executables in an insecure manner.
Right.
So how do we fix? I mean, is it really just monitoring? Because you really can't prevent it from. I mean,
technically, if they do it right, that won't happen. Right. Like that shouldn't be what you expect. But again, we didn't expect this other stuff to happen either, right? And it does. So what we're doing is we're kind of doing a defense in depth approach, and that's where monitoring kind of comes in. It's sort of you probably want to check what your system's actually configured to now, even though at some point in history maybe you did it right. Doesn't mean that that something didn't change that. And no, I don't know what would change that, but it doesn't hurt to actually make sure that your settings are what you think they are.
But I've seen it throughout my entire career of working with firmware in different instances on IoT devices, on all these things.
Well,
I apply
completely out of firmware. I got this on my
any
OS
kind
all
of
the time.
Oh, software too. Yeah. So really, any update.
All this is.
Once you update the software, goes in and changes configuration. I've seen it time and time again. It doesn't
technically have to be an update. So like if you look at this and you say, oh, I didn't install any firmware updates, so I must be okay. Well, yeah, unless you have like a system management application that actually knows how to change this. And maybe there
because
is
it's just is this setting that we're talking about is just an NVRAM variable.
It
And
doesn't, it depends on how it's exposed, but yes, like there is an
well, because
API to
NVRAM
change
variable,
these things.
yeah, but NVRAM variables also kind of have their own access controls that can be
Exactly.
applied to them, which we've covered somewhere. Somewhere we talked about those
Yeah.
in Eclipsium history. There's been book training. It's in our training material, and it's in some. I think it is some other presentations. But all we're talking about for this setting is an NVRAM variable, which can have a varying degree of protections and controls that dictate what can change that and what cannot change.
A lot of it comes down to, did you do it right? And the
Mhm.
problem is that it's not a one-time question. Did you
Right.
do it right in this release? Okay, cool. But you got 6 more after that
Mhm.
where you could mess it up. Did you do it right? Cool. But we're also using tools X, Y, and Z to manage these things, and any of those could mess it up. So
Right.
that's why we always look at monitoring as a critical item, because I can't tell you how many times I've looked at fleets of machines, and either I or somebody else thought they were configured a certain way, and then you go look at it and you're like, well, I guess not.
Yep. And this is something that I personally think without our software is a difficult thing to monitor, especially at scale. And it's monitored very similar to the way you would monitor, like, is secure boot enabled or not, right?
Yeah.
That's also, there are a number of different settings that come from your firmware or UEFI that you should monitor on a regular basis, that for all the reasons John and I just talked about can be changed, manipulated without your knowledge, unless you're monitoring consistently, continuously for these changes.
And that's probably where we get into the recommendations that we've got next, which
Yes.
is where, I you can go through all the specifics, but I like to step back and look at, in a general sense, what's going on. In general sense, you have suppliers that build various pieces, and you've integrated it in some place, and somebody else takes possession of the thing and does whatever to it, and it moves on and moves on. Eventually it gets to you. And what you need to figure out is, how do I believe that this machine is okay? Or this software is okay, or this whatever it is okay. And you only have certain things at your disposal. One of them is, well, I know who did it. I know my supply chain. I know who they are. I can hunt them down if they mess with me. Okay, that's cool. If you're really good at that, and you inspire enough fear in all of the people who are supplying you, that's cool. I doubt that you're going to pull that one off. But if you do, congrats. There is another idea that says, even if I'm trying to do that, I'm probably not going to succeed all the time. And there are things I'm going to check. And I'm going to know that if this is wrong, then I don't know what else is wrong. And so I'm going to use those as signs of whether or not I trust this thing. Some of those are really important. And if it's ever wrong, I'm actually going to stop what I'm doing and not use that thing. That's the sort of approach that we're recommending. And in general, that's what we recommend all the time. That's what our product is supposed to do. It's supposed to fit that need of telling you that this thing is actually okay, or it's as expected, however you want to say that.
Right. Yeah. And we also have a PowerShell script that we released to determine if you, one, have a Gigabyte motherboard, and two, tell you if that service is running in Windows. And that's what that script does.
Yes.
We also have a list of the affected models. And John, I think what you were speaking to was number 2 there, is to monitor those UEFI settings. And then you can also block access to those URLs and or host names in your environment as well. As
we're trying to find things that are under your control that you can do. And then that number 3 is one of the things that either at the host level or at the network level, you can, people know how to block URLs. That's at least something you can do.
Sure. There are some interesting things with Windows Platform Binary Table, in the interest of time. When I talk to my Microsoft friends about this, I get the answer like it's complicated, right?
Yes,
so, I mean, there are Windows Defender application controls that you can read about in that link there. So there are ways to
Lock it
improve the
down.
security, yes, of the WPBT process. There's also ways to disable it, but I do not recommend those. Like, try that at your own risk. When I ask folks that are experts in Microsoft Windows, I'm like, can't you just disable WPBT? And they're like, they kind of get that face like, don't do that. But if you want to, there's a link where you can go check it out if you wanted to pursue that path. I did want to just talk very quickly in general about the supply chain and how to deal with these risks that are coming into your environment from the supply chain. And I relate this to coffee, right? There's a lot of ways for people to get coffee. One, you could grow your own coffee plant and make all of your own coffee, right? On the opposite end of the spectrum, you could do no verification, no checking of the supply chain, do nothing yourself, and walk into the convenience store and buy a pre-bottled glass jar with a cap on it of coffee, right? And just go in the car and willy-nilly open it and start drinking it, right? Where I think we need to be in this analogy from an IT and security perspective is somewhere in the middle, where we're not validating and controlling everything by growing our own coffee, and we're not just going to the convenience store and picking up whatever. We're somewhere in the middle. We're verifying and then trusting. We have some processes that we rely on other people in the supply chain, in other companies in the supply chain, but we do some kind of validation for it. Now, this analogy is very nice because in some circumstances, yeah, you might actually grow your own coffee, right? You might create your own software. Cool. In other circumstances, you may go, I just want to go in the convenience store and grab a coffee, and do that similar kind of thing in your IT strategy for your company. And that's cool too. But I think most of the time we're in that middle ground where we have to, excuse me, verify and then trust.
I think that's a perfect analogy for what I was trying to explain.
Yeah, I thought that came out good in that particular slide in that analogy. So thank you everyone for attending today. I did want to say, like, if you liked this presentation, it's very similar to how we run our podcast. We've got, I think almost 11, no more than that, episodes of the Eclipsium podcast, Below the Surface podcast, that I do as part of my role here at Eclipsium. I interview all kinds of really awesome people. Scott Shefferman's the co-host. I'm going to start bringing on now folks internally, folks like John Lucades onto the show to have chats as well. So you can find it all at eclipsium.com/podcast. Melissa, back to you.
Thank you. We have actually exceeded our time, but I wanted to thank everyone again for joining us today. And I did get a couple questions during the presentation about the slides and the recording. And yes, we did record, and we will make all of this available. I'll be sending out an email tomorrow. You'll see it from me, Melissa Russell. I want to thank John and Paul again for another great webinar, and can't wait to see you all on the next one.
Excellent.
Thanks, everyone.
Thanks for having me.
Have a good day.